Hello, my name is Woo Hyun-jung, and I will introduce how we implemented a transform classifier to identify Trastuzumab binding antibodies for the HER2 protein with ESM embedding. Our goal is to develop a transformer-based classifier that can identify Trastuzumab antibody candidates binding to the HER2 protein using ESM embedding. The previous paper aimed to overcome the high cost and time inefficiency. In the study, the 10 residue CD3 sequence of each antibody was one encoded to classify whether it binds to HER2 protein. The study is meaningful in that it supplemented traditional antibody development method with AI and large-scale data. In the previous study, one-hot encoding was used to represent amino acid as a 20-dimensional vector. While this method is simple and fast, it does not capture the meaning or structural relationship within the sequence. Additionally, CNN learn local pattern between adjacent positions, which limit their ability to capture complex interaction across the entire sequence. To address this limitation, I proposed using 1280-dimensional embedding vectors from ESM instead of one-hot encoding and applying them to a transformer model. Transformers, based on the self-attention mechanism, can learn relationship between all positions in a sequence simultaneously. With such rich, high-dimensional input, transformer can learn patterns more precisely and potentially leading to improved classification performance. Embeddings corresponding to the 10 residue CDR3 lesion were extracted to form 10 multiple 1218 two-dimensional array. The label indicates binding status. The edit distance represents how many amino acids differ from the reference CDR3 sequence of Trastuzumab. Notably, sequences with higher edit distance are generally more difficult to predict and learn. This is an example of dataset. ESM embedding are high-dimensional with a wide range of value, including both negative and positive number, making normalization essential. So, we applied standard scalar. Samples with an edit distance of 10 are the most challenging cases, but they are relatively underrepresented in the dataset. To address this imbalance, we applied oversampling by replicating the edit 10 data 7 times. The current slide presents a visual diagram of the full model architecture. While the 1280-dimensional ESM embedding contains rich information, they pose risk of overfitting and increased computational cost. To address this, we applied a dense layer to reduce the dimensionality to 256, extracting only the most relevant features. ReLU function set all negative values to 0, which can lead to information loss. Since ESM embedding contains important information in negative values as well, we found that ReLU or mesh is more suitable for our model. Transformers do not understand the order of elements in a sequence. To address this, positional encoding is added to the embeddings to provide the model with explicit positional information. Multi-head attention enables the model to learn various relationships between amino acids simultaneously. Each amino acid attends to all other in the sequence, allowing the model to determine which residue to focus on. Each attention head captures different aspects, resulting in richer and more expressive representations. While self-attention captures relationship between residue, the feed-forward network defines the meaning within each residue's representation. Like this example, FFA combines different picture within each residue vector to extract more meaningful representations. Effectively, 256-dimensional input vector is transformed into a new dimensional embedding where pictures interact in more informative ways. The transformer architecture repeatedly stacks FFN and MHA layers. With each repetition, the model progressively refines the meaning of the embedding vectors. This iterative process allows the model to effectively learn representation that answer the key question. Does this sequence have the potential to bind to HER2 protein? Attention pooling assigned weight to input token based on their importance using self-attention to guide the pooling process. Multi-attention pooling captures diverse patterns across multiple attention heads, minimizing information loss. Pure AUC is a reliable metric for evaluating model performance on imbalanced dataset. A high pure AUC indicates that the model can make a great prediction without missing relevant positive case. At distance 1 to 9, pure AUC ranged from 0.98 to 1, indicating near perfect performance. At distance 10, pure AUC was 0.85 compared to 18.8 reported in the original paper. We believe that the slightly lower performance on ED10 samples is due to their higher complexity and relatively small number in the dataset. Despite using information-rich embedding vector, models' performance on ED10 remains slightly lower. We think that the model focuses more on learning from edit distance 1 to 9, where the data is more abundant and evolutionally closer to the original. In contrast, edit 10 sequences are both more complex and less, making them harder to learn effectively. However, the original paper used simpler representations, which we believe lead to looser, less stringent prediction. In contrast, our approach, despite being more complex, achieved comparable performance. Furthermore, our goal is to more rigorously select proteins that bind to Trastuzumab for experimental validation. From this perspective, our model maintains similar performance while making stricter prediction, which is desirable in real-world drug development. Future goal and plan: adjust the number of transformer blocks and modify the initial dense layer structure. Generate ED10 data directly using diffusion-based methods. Apply fine-tuning specifically for ED10 samples using the LoRa approach. With this strategy, we aim to achieve more precise selection of drug candidates that are well suited for experimental validation, surpassing the performance of existing studies. Thank you.